In this lecture, we are going to see how we can utilize the satellite data sets for analyzing the variability of rainfall at different scales. So to start with this lecture, let us look into why at all we need to measure the rainfall, why it is required. So first of all, for the survival of life on Earth. Secondly, rain is an important component of energy exchange, and this is one of the crucial parameters for the estimation of the hydrological cycle. This is one also important parameter for the analysis of the climate change and its impact on various variables, disasters induced due to rainfall, and agriculture. There are various methods to estimate precipitation, like we can use the ground-based radars. We can also use network of rain gauges or the satellites. All these three comes under the category of observations. Then we can also use the model output. That could be for the forecast simulations or the hindcast simulations using the numerical weather prediction models. So rain measurement system, each of the system having some advantages and disadvantages associated with them. So let's start with the rain gauge measurement system. So the advantages with the rain gauges are basically the true measurement of rainfall. So rain gauge provides the best estimate of the rainfall, and there are various disadvantages also with this method, like there is no coverage over oceans or remote regions. Rain gauge provides the point measurement. Therefore, whatever output we get from the rain gauges is not the representative of an area rainfall. Wind underestimates the rainfall, and there is a problem with the gauge design. So there may be some rain gauges of having different designs. Accordingly, we have to adopt the different calibration techniques also. Now the second method for the rainfall estimation is the radar. Advantages are radar provides us the rainfall in very high spatial and temporal resolution. We get observations in real time, but there are disadvantages also, like there is a little coverage over oceans or remote regions. There is an issue with the signal calibration, and rainfall, which is measured by the radar, is basically the indirect estimation of rainfall that is based on the reflectivity and rainfall relationship. Now, if we use model for the rainfall estimation, so there are certain advantages also, like we get the excellent space and time resolution, because we can decide when we are running the model simulations at what resolution, be it the spatial resolution or the temporal resolution, that can be decided by the user or the person who is performing the model simulations. An estimation of rainfall we get in the real time. And for the estimation of rainfall from the models, we include the meteorological context from other model fields like boundary conditions, initial conditions. There are various disadvantages also if we use the model output for the rainfall, like forecast based on model, but these are not the observations. So we can't compare the output from the models with the observations, because there could be some overestimation or underestimation. And the reason being is model may not simulate atmospheric processes perfectly. Now, when to use satellite rainfall estimates in real time? When we don't have the rain gauge or radar data sets available, when NWP model output, suppose we are running the model and we are not sure whether the output is reliable or not, we may go for the rainfall estimates from the satellites. For the evaluation of the model output or the model prediction, we can use the satellite-based rainfall data sets, and there are various typical situations. In those cases, we require the satellite data sets like the tropical convection, mid-latitude convection, storms moving onshore from seas, especially tropical cyclones, etc. For the monitoring of all these, we require the satellite data sets. Now, this is a typical picture which shows the estimating of the precipitation from various means, like we can monitor the rainfall from the satellites, radars, rain gauges. So in this case, you could see that there is a cloud and satellite is monitoring the cloud top. At the ground, we have the radar and the rain gauges. So rainfall which is falling from this particular cloud is not being collected by the rain gauges, because rain gauges are far apart from the location where the rainfall is pouring. Then the radar, it is actually a beam which is sent by the radar and reflected back to the receiver for the estimation of the indirect relationship between the reflectivity and the rainfall. Likewise, if we just look at the satellite is able to cover the entire top of the cloud. So each of the methods, as discussed earlier, also having some advantages and disadvantages. In this case, we can at least see that satellite is able to capture the entire cloud from the space. So if we use the satellite data sets, as shown in the picture also, it significantly expanded spatial coverage over land and ocean both we get from the satellites, which is not possible in the case of the radars and the rain gauge data sets. There is no issue of the beam block. This particular issue we face when we use the radar data sets. Like there is no interruption because of the mountains, buildings, or insects, because we are monitoring the rainfall from the top or from the space. There is a less need for calibration, often using only one instrument on board, such as GOES, and also instead having the calibration devices on board. And satellite data sets also supplements the ground-based radar and rain gauge estimates. Now the applications of the satellites for rainfall related studies. So there are various requirements. These requirements varies from the temporal scale. Like for short-term requirement, we need the rainfall data sets for the nowcasting of severe storms. For weather forecasting also we require the satellite based data sets. Initialization of NWP, we do use the satellite based data sets. River management and flood control. Then there comes the medium term needs like intra-seasonal variability. Suppose we would like to monitor the active and break rainfall spells, we can go for the satellite data sets. And also for agriculture, there are long-term needs like climate change and the hydrological plannings. For climate change, we may look into the flood and drought year that comes under the category of interannual variability of rainfall. Now there were various satellites. The main satellites which are listed here, like infrared sensors based satellite, can be utilized for the estimation of rainfall. The examples are GOES 11 and GOES 12, Kalpana 1, INSET 3D, 3DR. So now we have INSET 3D and 3DR datasets available from the portal MOSDAC. It's a ISRO data portal from where you can get the data sets for the meteorological applications. There are the microwave sensor based satellites like DMSP SSMI, NOAA AMSU-A, AMSU-B, Aqua AMSRE. TRMM is having one microwave sensor on board, that is TMI. TRMM microwave imager is the name of the sensor. Then there is a sensor called GPI on board GPM. Now TRMM is out of phase, so we have the data available from GPM for the rainfall monitoring. There are satellite radars also. So we have TRMM-PR. This is precipitation radar on board TRMM. This mission is out of phase, so precipitation radar data sets from TRMM is available till 2014. Then we can utilize GPM, DPR data sets. This is the dual frequency precipitation radar on board GPM satellite. So now we have data sets available from GPM specifically for the satellite radar. And if we are interested for the monitoring of the rainfall from the infrared sensors, specifically over the Indian region, we can go for INSET 3D or 3DR. Apart from that, we have these satellite estimates available from the microwave sensors. These microwave sensors are on board the polar satellites. So all the satellite listed here, DMSP, NOAA, Aqua, TRMM, GPM, are all the polar satellites, and TRMM was one of the low inclination satellite. Now the satellite based rainfall estimation methods. The retrieval of the rainfall from the satellite measurement are generally categorized into LEO and GEO as per satellite's orbit. So low Earth orbiting satellites or the geostationary satellites, there are various methods associated with them depending upon the type of the sensor. So retrieval algorithms are typically classified on their observing spectrum. For example, suppose we are using the visible and infrared band data sets, then it comes under the category of visible and IR based rainfall. Then there are passive microwave methods, active microwave methods, all the multispectral rainfall, that is use of one or more of these individual spectrums. We can combine the estimates from visible IR sensors with the passive microwave data set to get a multispectral rainfall. If the methodology uses multiple satellites or other information such as radar or rain gauges, that is classified as a blended technique. So there are various methods available for the rainfall estimation, but there are various issues that we should keep in our mind, like all the clouds are not the precipitating clouds. At times, processes responsible for the growth of tiny water droplets are not strong enough. And third point is, if air below the cloud is very dry, so rain falling from the cloud waste may get evaporated before reaching the surface. So all these 3 points we need to keep in mind, because if we use the satellite data sets, satellite basically monitor the cloud top if we are using the infrared and visible bands. So the information that we are getting from the cloud top based on the cloud top characteristics, be the temperature or its albedo, if the temperature of the cloud top is cool enough, we would say that there may be a rainfall out of it. But if air below the cloud is very dry, then rain falling from the cloud base may get evaporated. Now the visible sensors, let's discuss the special characteristics of these sensors. Like if we use a visible sensor, so the visible channel of the satellite measures the light using the same wavelength as the human eye. So objects with higher albedo appear brighter on the satellite image. Objects with lower albedo appear darker on the satellite image if we are using the visible sensor. And visible satellites are only available during the daytime because it requires the solar radiation for the illumination of the objects. So we have the estimates available only during the daytime if we are using the visible sensors. Here are the good uses of the visible sensors, and that include thunderstorm features, snow cover, fog, marine layer clouds, hurricane features, other large-scale features can be monitored using the visible sensors. Now come to the infrared sensors. So infrared satellite measures the radiation output from the Earth into space. In other words, it measures the temperature, and one can infer the clouds based on the different temperatures being measured. Here are the good uses of IR sensor, that includes nighttime satellite use. Unlike visible sensor, we have the data sets available from the infrared sensor 24/7 because we can use the satellite during the nighttime also. We can use the IR based images for the monitoring of strength and weakness of convection, approach of the cold air mass depending upon the temperature of this particular mass. We can identify whether a cold air mass is approaching towards a particular region or not. Cyclone development can also be monitored using the infrared sensor. Turf and ridges within the jet stream can be identified using the IR sensors. Hurricane strength and analysis can be done using the IR sensors. Now the rain measurement system. As I told you in the previous slides, that there are various methods for the estimation of the rainfall. So let's start with the visible and IR sensor. So these sensors are available both on the polar satellites and the geostationary satellites. And if we use the visible and IR sensors onboard geostationary satellites, we get several advantages that we don't get in case of the polar satellites. So visible and IR sensors, if onboard on the geostationary satellites, here are the advantages, like good space and time resolution we get from the visible and IR based data set, observations in near real time, it samples the ocean and remote regions, and geostationary satellite provides the consistent measurement system because geostationary satellites are fixed with respect to the one position on the Earth. So if we talk about the INSET satellite, it is fixed with respect to the location of our Indian subcontinent. So throughout the day and night, 24/7, we get the measurement from the geostationary satellites onboard visible and IR sensors. But there are disadvantages also. because the rainfall that we measure from the visible and IR based techniques that measures the cloud top properties instead of rain directly. So it is kind of an indirect method. And if we use this method, we may mistake cirrus for rain clouds. As I told you in the beginning, that we also need to keep in our mind that all the clouds are not the rain bearing clouds. Since the IR and visible channel based sensors use the cloud top information, and cirrus clouds are the clouds which are cold clouds. So IR sensor would infer there is a low temperature at the cloud top, and you may have some assumption about the rainfall, but cirrus clouds are not the rain bearing clouds. So we may mistake for that. And visible and IR sensor are also not able to capture the rainfall from the warm clouds, because ultimately these sensors measure the cloud top properties, and particularly for the IR it measures the temperature of the cloud top. In case of the warm clouds rainfall processes, the cloud top is not cold enough. Therefore, we may miss the signature of the warm rain from the visible or IR based techniques. Now the infrared theory. So infrared based rainfall estimation is basically based on the relationship between the cloud top temperature, cloud top thickness, and precipitation. So colder cloud top temperatures imply the higher and thicker clouds, which imply heavier precipitation, because we are looking at the cloud top. And then there is a relationship between the changes in cloud top surface and precipitation with time. Suppose we are given the multi-temporal images from the infrared sensors. We can monitor the multi-temporal images and we can see whether the cloud is a growing cloud or it's a decaying cloud. So vertically growing clouds are associated with precipitation, while decaying clouds are not. So how do we measure this? Suppose we are monitoring the multi-temporal images. So the cloud top temperature, if it goes down with time, it means the cloud top is cold enough now with time. So we can say that there will be precipitation. And in other case, if the cloud top temperature is not going down, is actually increasing, so we would say that this particular cloud is a decaying cloud, because the towering clouds are basically the clouds where the temperature is low enough. As you may be knowing, that temperature decreases with height. So heighted clouds are having colder cloud tops. So in case of the infrared theory, we measure the cloud top characteristics and accordingly we infer whether there will be precipitation from this type of the cloud or not. So basic assumptions, if we are using the visible or IR based algorithms. So assumption is that the cloud top temperature brightness is related to the cloud height, which in turn is related to the cloud thickness and then to the rainfall rate. So colder and brighter clouds are associated with heavier rainfall, and warmer and less bright clouds are associated with light or no rainfall. So this method is basically a reasonable assumption for convective clouds which are brighter and also colder. But this method is basically a poor assumption for stratiform clouds. Stratiform clouds are basically the warm clouds but rain bearing. And then there are the cirrus clouds. These cirrus clouds are the cold clouds, but these are not rain bearing clouds. There are various estimation techniques based on the visible and IR sensors. So Barrett and Martin divided these techniques into 4 categories. So first category is the cloud indexing technique. So in this technique, what we need to do? We need to assign a rainfall value to different cloud types that is identified in satellite images. So Arkin's method or the ghost precipitation index GPI is also based on cloud indexing technique. Then there is another technique called life history technique, which is based on the cloud life cycle. Suppose we have the multi-temporal images, accordingly we can identify by estimating the cloud top temperature whether the cloud is a growing cloud or decaying cloud. So we basically use here the life history of the clouds. Then there are the bispectral technique. So cold and bright clouds, using visible and IR observations, we can infer whether the cloud is a rain-bearing cloud or it's not a rain-bearing cloud. Then comes the cloud model technique. So we can use the conceptual cloud models and IFFA, auto estimator or hydro estimator methods for the estimation of rainfall from the satellites. Next is GPI, which is basically the cloud indexing method. In this method, basically what we use a large temporal and spatial scale rainfall measurement with 3 hourly thermal IR images. We need to identify a pixel if it is having a temperature or the brightness temperature less than or equal to 235 Kelvin. If the brightness temperature of a pixel is less than 235 or equivalent to 235 Kelvin, then that particular pixel may be the precipitating pixel. And the fractional cloud cover in a grid box is a fraction of raining pixels in that box. So fractional cloud cover is related to the 24-hour rainfall by the equation called K multiplied by fractional cloud cover, where K equal to 71.2, it's a constant. This constant is fixed. If it is multiplied by the fractional cloud cover, we may get rainfall in millimeter per day. So same value of the K is used by the IRCN for the Indian region also, that is 71.2. Suppose we have the data sets available from INSET satellite, particularly for the IR sensors, we can use this 71.2 as a factor to multiply with the fractional cloud rainfall in millimeter per day. This is the GPI technique. Data set from this technique are also available on the ISRO meteorological portal mosdec.gov.in. So here is the relationship between the cloud above 10 km on the x-axis, and on the y-axis we have the radar estimates of the rainfall. So based on this method, we get some kind of the relationship between the cloud above the 10 km and the rainfall on the corresponding to the pixels wherever we are estimating the fractional cloud cover. So based on this relationship, one statistical relationship may be developed, which is giving you the relationship between the rainfall and the cloud above 10 km. So from the satellite data sets, we can have the information about the fractional cloud cover. And if we know this equation, we can estimate rainfall from the data sets where we know the fractional cloud cover. Based on this method, this global annual rainfall is developed from 1986 to 1995. As told you earlier that this such kind of the method are able to capture the large scale features and the convective rainfall. So in this picture, and if we match the color distribution in this special pattern of the rainfall across the globe with the color bar given below, you can see that there is a band which is extending across the globe that is called the ITCZ, Intertropical Convergence Zone. So such kind of the large scale features may be measured if we use the GPI based rainfall estimation. Now the advantages of satellite rainfall estimation with visible and IR techniques. We get the uniform and continuous coverage over land and oceans. We get large spatial coverage, we get the uniform resolution, we get the continuous observation capability over evolving time and near real-time availability of data sets. But there are several disadvantages also. So this is also one of the indirect method, as the rain is estimated by observing the top of the cloud. The algorithm derived for a specific place and rain type may not be applicable to other regions. The convective systems smaller than the size of the pixel often go undetected. Indirect relationship between the cloud top temperature and the rainfall, or the cloud brightness and the rainfall, is not simple. It has been observed that not all the cold clouds are the rain bearing clouds like cirrus clouds, and also rain always does not come from the cold clouds. The example is warm rain processes. So apart from the visible and IR sensors, we can also use the passive microwave sensors for the estimation of the rainfall. So early weather satellites mainly relied on the visible and infrared sensors, And if you use the microwave sensors, so we measure the energy at longer wavelength from 1 to 300 gigahertz or 32.1 centimeter range. So on the figure, the electromagnetic spectrum has been shown here. And on the bottom x-axis, you can see the wavelength in meters. On top, the corresponding frequencies in hertz are written. So microwave channels located in window regions observe both land and oceans. So these channels which are located in the absorption regions observe the atmospheric constituents and clouds. So we use these wavelengths for the estimation of the rainfall from the passive microwave sensors. Here the absorption bands are shown in the electromagnetic spectrum and absorption by atmospheric gases for the microwave region. And here is a rainfall estimation based on emission and scattering based techniques. So the estimation of rainfall from the passive microwave sensor is divided in two methods. One is the emission based method, the other one is the scattering based. So thereafter comes the combined and also the radiative transfer. But let's look into the when we are directly using the microwave frequencies for the estimation of rainfall. So low frequency, suppose we are using the frequencies less than 30 gigahertz or so. So the technique which is associated for the rainfall estimation in this category comes under the category of emission based method. And this method is more applicable over the oceanic region. There is another method called scattering based technique. This technique we use for the high frequency microwave frequencies like 80 gigahertz or higher. And this particular method is applicable over both ocean and land. Then comes a combined technique. If we combine the emission and scattering based method, we get the combined algorithm, where we can make use of the advantages of both low and high frequencies for the estimation of rainfall. And we can also use the radiative transfer model and the profiling to get a priori data set for the development of the rainfall estimations. TRMM based rainfall also is based on the radiative transfer model and the profiling algorithm. So passive microwave sensors are available on board polar orbiting satellites. However, the visible and IR sensors are available on board geostationary as well as polar orbiting satellites. So in case of the rainfall measurement or the estimation or the monitoring, we require the continuous monitoring of a atmospheric process. So in that case, we go for the geostationary satellite. Suppose we have the passive microwave data sets available from the polar orbiting satellites, we can also estimate the rainfall using the scattering based method or the emission based method. We may also combine these two methods to get the combined rainfall estimation algorithm. So there are various advantages if we measure the rainfall using the polar orbiting satellites passive microwave sensors. And these advantages are, it samples the remote regions, consistent measurement system, and the technique or the algorithm which is based on the passive microwave sensor is more physically. It is more accurate than visible and IR estimates. But there are several disadvantages also. It gives us the poorer time and space resolution. And it's not a direct measurement of rainfall. Again, we have to combine the methods like scattering from the ice crystals or the emission from the water content available within the clouds. But the relationship between the water content in the cloud and the rainfall from this is not direct. And also the ice crystals, they do scatter the microwave emissions from the Earth's surface. This relationship is also not direct relationship. So this does not capture the rain from the warm clouds over the land. This is also another third disadvantage from the passive microwave sensor. Now the microwave theory, basically, if we use the relationship between the ice in cold clouds and precipitation. So ice scatters the terrestrial radiation back down to the surface, making microwave imagery appear cold where ice clouds are present. Then there is a direct relationship between the water content in the clouds and precipitation. Water in clouds emits microwave radiation and making microwave imagery relatively warmer where high water content clouds are present. Suppose you are given the microwave images for the high frequency channels as well as for the low frequency channels. Low frequency channels are generally used to measure the emission from the water content within the cloud that emits the microwave radiation. So suppose you are given the multi-temporal images from the low frequency channel of passive microwave sensors, and if you monitor that, suppose there is a enhancement in the emission over a particular location, you may infer that cloud may be present there because cloud are the water content clouds. So therefore there will be high emission from the water content within the cloud that can make the imagery warmer over that particular location. And on the other side, if you are measuring the rainfall from the microwave sensors using the high frequency channel, these high frequency channels are sensitive to the ice crystals. So ice scatters this terrestrial radiation. So there is an emission which is coming from the Earth's surface in the microwave region. This microwave radiation is further scattered by the ice crystals present within the clouds. So there is a reduction in the net microwave imagery which will be recorded by the satellite sensor. So over that particular place, wherever the ice crystal bearing clouds are present, if you monitor such location using the multi-temporal high frequency passive microwave sensors, you would find that over that particular location there is a dip in the outgoing emission which is being recorded by the sensor. So using these two methods, we may monitor the rainfall based on the both emission and scattering based methods. So there is a sensor called SSMI onboard DMSP which uses this scattering based algorithm for the estimation of the rainfall. This algorithm is also known as the NOVA algorithm. On the top, there is an equation called scattering index, SI, that may be estimated using the microwave frequencies like 19 gigahertz, 22 gigahertz, and 85 gigahertz. So basically, scattering index is the difference between the 19 gigahertz and 22 gigahertz. Just make some factor called capital F and then subtract the estimated 85 gigahertz brightness temperature that is being recorded by the satellite sensor. So once you estimate the scattering index, that is basically the indicator of the presence of the ice crystals within the clouds. Thereafter, a relationship between the rainfall and the scattering index may be developed. And in this case, suppose we are to develop the relationship between the rainfall and the scattering index, we require the rainfall data set either from the rain gauges or the radar to have the estimation of the coefficients A and B. So these are the coefficients like A, B, A0, A1, A2, A3. These are the region specific coefficients because rain bearing system from place to place are also different. So the same coefficient cannot be used for all the locations across the globe. So particularly we need to develop the regional algorithm and then we can estimate the A0, A1, A2, A3 for the estimation of scattering index, and thereafter the coefficients called A and B using the multiple regression technique. And then once we develop this relationship and we have the coefficients with us, we can estimate rainfall using the passive microwave frequencies. So in this figure, this a special map across the globe of the rainfall estimated from the SSMI sensor is shown. So as discussed earlier, like there are various sensors on board the satellite, particularly the polar satellite, which are the passive microwave sensors like SSMI onboard DMSP, AMSU, AMSU onboard NOAA, TRM, TMI onboard NASA. So this is NASA experiment. TRMM is the satellite, TMI is the sensor. So the schematic shows here the rainfall distribution which has been estimated from these three different microwave sensors. So since these sensors, the microwave sensors are available on board the polar satellites, so depending upon the satellite pass over a location, if we estimate the rainfall and then just compare the output from these satellites, that may not match because these are the polar satellites. So satellite pass over a location may not match with the pass of the other satellite. So in these cases, we may miss some signatures which may be captured by the other satellites. So here you can see that the rainfall from SSMI has been measured on 3rd November 2001 at 11:51 UTC, whereas the NOAA AMSU measured the rainfall over the same location at 12:10 UTC, and TMI sensor measured the rainfall over the same location at 6:40 UTC on 3rd November 2001. So this basically, if we compare the rainfall output from these satellites, the polar satellite sensors, this may not match because the pass over these locations of these satellites is different from each other. So far we have seen that we can utilize the microwave based methods like emission and scattering. At the same time, we can also monitor the cloud top temperature from the IR based method. So in this slide, the three images are shown here. One image is from the microwave low frequency channel. The other image from the microwave high frequency channel. So high frequency are basically sensitive to the ice crystals. So there will be a scattering of the immediate microwave emission. So there will be a depression in the image if ice crystals are available. Here we are using the microwave low frequency channel. So these low frequency channels like 19 gigahertz or 22 gigahertz are more sensitive to the water content in the cloud. But in this case, the ice crystals are available. We can see the depression in the image. At the same time, there is an enhancement in the radiation, which is being recorded by the satellite sensor because the water content is also available. Suppose there is a water content available within the cloud. So it will enhance the emission in the microwave region. So there is a microwave emission from the Earth surface that is coupled with the emission by these water. Ultimately, we get the enhanced microwave emission from such kind of the features at the satellite sensor. So if we compare these two images that we obtain from the microwave based frequencies with the IR based cloud top temperature. So if we see the color bar, this red color is for the low temperature, low cloud top temperature. So the feature here, the dip in the microwave emission in the high frequency channels, enhancement in the microwave emission in the low frequency channels, that is coupled with the low cloud top temperature. So these three images coupled together suggest us that this is the cloud where sufficient ice crystals, water content is available. This is the heighted cloud because the cloud top temperature is also very low. So if we combine the method, that is the microwave based methods and also the IR based method, we get the better estimates of the rainfall. So such kind of the estimation of the rainfall, then when we combine the estimates from the geostationary and passive microwave rainfall, so we get the best features. Like we get the good space time resolution of geostationary estimates because we are getting the IR based output. At the same time, we are also using the microwave estimates for the scattering and emission of the microwave energy due to the presence of the ice crystals as well as because of the water content. So this method provides us a better accuracy. So we are getting both advantages if we combine the best features of IR and microwave. So based on these methods, the algorithms are available. This is GMSRA and IMSRA. So GMSRA is basically the ghost multispectral rainfall algorithm and IMSRA is the inset multispectral rainfall algorithm. So data sets based on IMSRA are also available on ISRO portal mosdec.gov.in. Apart from that, the data sets based on the blended technique can also be developed, where we can combine the rainfall estimates from the satellites with the rain gauges. So one such product is the GPCB, which is available at various resolution. Here the picture is shown for the 2.5 degree monthly resolution data sets. Apart from that, the daily data set from GPCB are also available. And this GPCB based precipitation is available from 1988 to till date. These images are the older images. Here the date is shown till 99. And in this case, this GPCP based method is able to capture the ITCZ, Intertropical Convergence Zone, which is a blended technique based rainfall estimation. Now the monitoring of rainfall variability. So before we start the monitoring of the variability, let us look into what kind of the variabilities are available at various scales that we need to monitor using the satellite data sets. So first of all comes the interannual variability of rainfall. So variations on the annual cycle of the rainfall producing the anomalously wet or dry years, or in other words, the flood and drought years. So generally, such kind of the variability is influenced by the sea surface temperature variations that is associated with ENSO or inherent variability in the Indian Ocean. So such variations we can monitor over a larger scale. These are the variabilities which are associated with the flood and drought years of the Indian summer monsoon. Then comes the intra-seasonal variability. Intra-seasonal variability is basically the variability that we observe within a season that lead to a 20 to 40 day droughts or flood periods. These are the drought and flood periods are known as the active and break rainfall spells. Suppose we want to monitor such spells, we may go for the satellite data sets. Then comes the diurnal variability. So rainfall fluctuations that happen during the day and the variations in the day-night cycle, that is called the diurnal variability. And then the extreme rainfall events, cloudburst events. So extreme rainfall events or the cloudburst events occur only 5% or less of the time. A cloudburst is an short span of time but is capable of creating flood-like conditions. According to IMD, rainfall rate equal to greater than 100 millimeter per hour may be considered as a cloudburst events. So all these four variabilities may be monitored using the satellite data sets. So I start with the interannual variability. So here the TRMM data set, that is the TRMM 3B42 version 7 dataset, had been used here for the estimation of interannual variability of monsoon season rainfall over India. So on the left hand side, the standardized normalized precipitation anomalies are shown. So based on the standard definition given by Parthasarathi and Mule, the normalized rainfall anomalies which goes above +1. So those years may be considered as a flood year. Likewise, whenever these standardized or the normalized anomalies are less than -1, those year comes under the category of drought years. So in this picture, we can see that there are the years like 2000, 2002 and 2004. Also 2009. All these 4 years are having the normalized unit of the order of -1 or less than that. So all these 4 years comes under the category of drought years. Likewise, as per the definition, the normalized unit for 2 years like 2006 and 2011 is +1 or higher than that. So these years are the flood years of the Indian summer monsoon. Further to this, we can also utilize satellite data sets for the variability of the rainfall for the contrasting monsoon conditions like flood and drought years. So here the power spectrum of the composite of flood and drought years has shown here. So composite means we can couple all the flood and drought years and then estimate the power spectrum and compare them with each other to identify the causes responsible for the contrasting monsoon conditions over the Indian region. So here the red power spectrum is for the drought years, the blue power spectrum is for the flood years. Drought years, as you can see, that the maximum power frequency is available corresponding to higher time period. So for the drought years, we get maximum variability corresponding to higher time period. On the other hand, the variability during the flood years is associated with the shorter time span. So such kind of analysis is possible using the satellite-based data sets. Then comes the intra-seasonal variations. So active and break rainfall spells comes under the category of intra-seasonal variability of Indian summer monsoon. So we can identify the active and break rainfall spell using the satellite-based data set. So again here the TRMM 3B42 V7 data sets had been utilized for the identification of active and break rainfall cycle. As per the standard definition given by IMD and also by Rajivan et al. In 2010, so active and rainfall spells have been estimated here. In this case, the active and break rainfall spell are shown here for a particular year of 2009. And as per the definition, if the area average daily rainfall anomaly standardized by its own daily standard deviation is less than -1 or +1 for successively 3 days or more, that spell may be considered as a break or active spell of the Indian summer monsoon. So in this case, since we are utilizing the satellite data sets, we need to do a sensitivity analysis to identify whether our satellite data set is able to capture the active and break spells correctly. So in this case, we have kept the threshold at 0.5 for the estimation of break and active rainfall spell during the year of 2009. So if we just see these negative anomalies, we can see there is an extended negative anomaly spell during the year 2009. This was one of the longer break spell which were responsible to make this year 2009 as the drought year of the Indian summer monsoon. So here in this picture, the spatial pattern, here we can see the temporal evolution of the rainfall anomalies during a year which was a drought year, and the reason being is the longer break spells during this season which were responsible to make this particular year as a drought year. And if we compare that with the spatial pattern of the rainfall during active spells and the break spells, what has been done here? Basically the active and break rainfall spell has been estimated for the past 13 to 14 years, and only the active spells have been combined together to check the spatial pattern of the rainfall, and thereafter the spatial pattern of the break spells have also been developed. And if we compare these two patterns, there's a high contrast between these two patterns. So during the active spells, we can see there is a high rainfall over Indian region, particularly along the Western Ghats, over the Central Indian region, along the foothills, and also over the Northeast Indian region. On the other hand, if we compare this pattern with the break spells of Indian summer monsoon, this is the composite. Composite means it's a combination of various years. So you just estimate the break spells of all the years over the last 10 to 14 years, then combine them together to have this special pattern of the break rainfall spell. So in this case, there is a larger region over Indian subcontinent, which having the lower rainfall, that is within the range of 0 to 5 millimeter per day. But in case of the active rainfall spell, the high rainfall, we can see during the active spells that the high rainfall is ranging from 15 millimeter per day to 30 millimeter per day. So there is a huge contrast between the spatial pattern of the rainfall, and we can also say that the active and break spell conditions may not be homogeneously distributed across the Indian region, but there are several regions which are responsible to make one particular year or the other as a flood or drought year, depending upon the number of active spells or the number of break spells during the year. So here is a seasonal rainfall and frequency of extreme rainfall events. So extreme rainfall events can also be estimated using the satellite data set. So in this picture, the spatial pattern of the seasonal mean rainfall over the Western Ghats has been shown here. So this is developed based on the TRMM data set at the resolution of 25 km by 25 km. Here color bar indicates the rainfall in millimeter per day. So in this picture, we can see that there are three different states in the Western Ghats region along with the Goa. So there is Maharashtra, Karnataka, Goa and Kerala. And if we compare these four locations, the intense rainfall is accumulated near the coastal Karnataka region, followed by Maharashtra and then Kerala. So maximum rainfall is received by the Karnataka region, coastal Karnataka region. Then comes the Maharashtra region. So based on this satellite data set, we also have developed the map of the number of extreme rainfall events along the Western Ghats region. So this is the special distribution of heavy rainfall event. These are the heavy rainfall events on the left hand side. On the right hand side, we have the extremely heavy rainfall events. So in this case, we have taken this threshold greater than 120 millimeter per day, but less than 150 millimeter per day for the heavy rainfall events. And if we compare this particular image with the seasonal mean rainfall, you would find that the heavy rainfall events are also higher along the Karnataka region, the coastal Karnataka region. But if we compare this special pattern of the seasonal mean rainfall with the extreme rainfall events, you would see that the extreme rainfall events are more along the Maharashtra coastal region. So this is the basically special difference in the number of events coming under the various categories. Here we have the seasonal mean rainfall. This is the amount of the rainfall which is received during a season. And here we have the number of events which are falling within this range. These are the number of events which are falling in the range of rainfall greater than 150 millimeter per day. So there is a special variability. So the region which is receiving the maximum mean monsoon rainfall may not be directly connected with the region where we have the maximum number of the extreme rainfall events. So Karnataka is receiving the maximum number of the extreme rainfall events. For details, I have referred various papers here that may be seen for details on the estimation and the methods associated with this analysis. Further to this, we can also utilize the satellite data sets to find out what is happening over the recent years, particularly for the distribution of the extreme rainfall events. So in this case, the rainfall distribution has been shown for the northwestern Himalayan region, which is vulnerable for the heavy rainfall events. So here the rainfall data set from the GPM is available for the past 20 years. This is particularly the IMERGE data set, which is a combination of TRMM and GPM. This data set is available at 10 km by 10 km resolution. And over the last 22 years of the time period, if we just look at the special distribution, we would find that in the recent 10 years, the rainfall amount has been increasing. So you can see the various red patches here. The amount of the rainfall has been increasing over these locations. Like there is a region, it's quite extensive region in the Uttarakhand region, Uttarakhand state, where the rainfall is increasing in the monsoon season in the recent 10 years. And the dots, the black dots are shown here. So there is a significant increase over these locations. At the same time, we can also see that there are the blues here. These blues are corresponding to the decrease in the monsoon season rainfall. So changes in the amount of the rainfall is not homogeneously distributed across the region. Some of the regions are witnessing the enhancement in the monsoon season rainfall in the recent 10 years. At the same time, there are few locations which are also witnessing the reduction in the monsoon season rainfall. However, there are more locations where we can see an enhancement, particularly over the Jammu Kashmir region, Ladakh region, parts of Himachal Pradesh, and an extensive region in the Uttarakhand. So based on the percentile method, we also have developed here the map for the rainfall intensities associated with various percentiles. to show the amount of the rainfall that is received in different categories over the NWH region. So 3 maps are shown here. One is for the heavy rainfall events that fall up to a range of 98th percentile of the rainfall data set. Then these are the very heavy rainfall events that are corresponding to the rainfall intensities which fall within the 99th percentile. Then we have the extremely heavy rainfall events or the cloudburst events. That is for the 99.99th percentile. So in this case, you would note that there are more number of extremely heavy precipitation events along the foothills or at the lower elevation. Over the higher elevation, we generally receive the snowfall. And if we compare the pattern of the rainfall over the last 20 years and by dividing the dataset in 2 years, you would see, however, there are the locations which are showing an increase in the amount of the rainfall during monsoon season. This is the seasonal mean. But if we go with the event wise and compare this PDF of the 2 time period, like first 10 years and the last 10 years, towards the tail, the number of events corresponding to heavy rainfall events are actually decreasing in present day or the recent 10 years as compared to the previous 10 years. Because here the blue curve is corresponding to the previous 10 years. This red curve is for the recent 10 years. So if we compare the number of events corresponding to these 2 curves on the y-axis, you would find that for a particular intensity of the rainfall, suppose 350 millimeter per day, the number of events for the recent 10 years are less than the number of events in the previous 10 years. So that's how the rainfall pattern is changing in such a way. Seasonal mean rainfall is witnessing an enhancement over NWH region, but number of extreme rainfall events corresponding to the heavy rainfall intensities are actually decreasing. So such kind of the final scale resolution data set is available only from the IMERGE data set. Apart from that, you may also go with the insect based rainfall like HE rain or the IMR rainfall. So in those cases also we are getting very good spatial resolution, and such kind of analysis can be done to have a fine scale structure of the rainfall characteristics over this vulnerable states of India. Here is a special distribution of number of extreme rainfall events. In the previous picture I have shown you the intensity. So more intense events you could see in the category of 99.99 percentiles. These are the intensities which are actually located in the foothills or the lower elevation ranges. And if we compare the number of events, sorry, I missed the slide, 1 second. So if we just count the number of events corresponding to these intensities, in every range we have different intensities. We have the special map of these intensities. We just need to count the number of events which are falling within these ranges. You would get such number of events. So based on these special pattern, we also know the number of events or the locations where there is a more occurrences of the extreme rainfall events. So high frequency of extreme rainfall events over region with less than 3000 meter elevation. So most of the events are located within the lower elevation ranges as compared to the higher elevation ranges. And Uttarakhand experiences higher number of extreme rainfall events. You can see this special distribution of number of events. So Uttarakhand is a region which is more vulnerable for the extreme rainfall events than the Himachal, Jammu and Kashmir and Ladakh region. Kangra, Hamirpur, Sirmaur, Nainital, Udham Singh Nagar and Champawat. These are the districts which are highly prone to the extreme rainfall events in the northwestern Himalayan region. Now the next variability, that is the diurnal variability. Diurnal variability can also be monitored using the satellite data set, which is not possible in case of the rain gauge data set, because from the rain gauges we get the data set at every 24 hours. So we get the daily rainfall data sets from the rain gauges. And if we use the AWS, the automatic weather station data sets, these are available at a very high temporal resolution, but there is a Scarce coverage of AWS over the northwestern Himalayan region. Rain gauges are also having very low density over the NWH region. So therefore, if you want to analyze the diurnal variability of the rainfall over such a complex mountainous terrain, we may opt for the satellite-based data set. So here the diurnal variability has been analyzed for every 3 hours for a long-term data set from the TRMM satellite. And it has been noted from this analysis that usually extreme rainfall events occur from late night to early morning hours, because you can compare the intensity shown here in the color bar. So during the late night to early morning hours, there are various red colors that you can relate with the color bar. So extreme rainfall events occur from late night to early morning based on this diurnal variability. So there is a selection of the temporal period for the occurrences of the extreme rainfall events. And then comes the orographic rain peak. Orographic rainfall, which is basically associated with the warm rain processes and occur along the windward side of the mountains. So these are generally observed in the afternoon to evening hours. But these rainfall events are not intense enough to give rise to extreme rainfall events. So to this information add with this distribution of the extreme rainfall events, here we get the information about the intensity of the extreme rainfall events. From this figure, we get the information of the number of extreme rainfall events. And from the diurnal variability analysis, we get the information, the time period during which we can experience the extreme rainfall events. So if we couple together all the information, we get a very rich information based on the satellite data sets, specifically for the extreme rainfall events. Now here is the application of the satellite data sets for the progression of the or the movement of the rain bands prior and after the cloudburst events. So in this particular case, the inset based data set, that is the IMSRA based data set, IIMR, has been used for the analysis of the rain band progression across the northern region of India. In this case, you can see that at 9 GMT on August 5, there was no rain-bearing clouds available in the Leh region. After 3 hours from this event, you can see there is a rain-bearing system which is moving towards the northwestern region. After 3 hours from this event, there is a dissipation of the rain-bearing system, but is also confined over a smaller location, and which is situated along the northern boundary of the Indian region. This system further moved towards the Leh region around 18 GMT. And this is the time of the cloudburst event on August 6. This is the intervening night of August 5 and 6. So this is the 21 GMT, August 5. This is the intervening night as per the Indian Standard Time. And this was a time of the cloudburst over the Leh region. So you can see a darker patch here, which is corresponding to the heavy intensity rainfall over the Leh region during the time of the cloudburst event. So after 3 hours from this event, this high intensity rainfall system is dissipated from the Leh region and it is moving towards the southwest region of neighboring country. So if we use the multi-temporal images for the monitoring the prior and after conditions of a cloudburst event, we may go for the geostationary satellite-based IMR dataset. This particular type of the analysis gives us the information that from where the convection was forming, how it was coming to the Indian region, what was the speed of the rain-bearing system, and using such information, we can have some idea about the propagation of the system and also the probable location. However, we need to expand this work further to get better idea about the nowcasting. But this is the building block of the nowcasting techniques. Now, likewise, this IMR product, the IMRH data set from the GPM can also be analyzed for the rainfall distribution prior and after the cloudburst event over various locations in the mountainous region. So here, one case has been shown for the Ganderbal region. The cloudburst event over this region was reported around 15 GMT to 18 GMT on 16 July of 2015. So the movement of the rain bands can be seen that earlier there was a high rainfall in the Uttarakhand region, then this moment there is a movement of the rain band, and then further there is an intensification of the rainfall over the Ganderbal region, and after the cloudburst event there was a dissipation of the rain bands. Likewise, in this case, we can also see the amount of the rainfall in the Sonmarg cloudburst event of the year 2015. Again, in this case, the IIRS dataset had been used. And there's a movement of the rain bands can be seen here. This is the time of the cloudburst event over the Sonmarg region on 16th of July. The short-lived event, they are confined over a very smaller region, and they last within minutes to hour, half an hour or so. So for the monitoring of such kind of an event, we need a special picture at higher spatial and temporal resolution, which is possible in case of the satellite-based data set. So there is a further application of the satellite data set for the monitoring of the progression of monsoon. So in this picture, the progression of monsoon 2022 has been shown here. And here the data set from INSET satellite. This is a GPA data set had been used. And this picture is basically showing the cross equatorial flow. This is the monsoon flow, and the stronger winds are carrying the moisture over the Indian region, which is responsible for pouring rainfall across the Indian subcontinent. So these images are available till the end of June in this particular presentation. So here you can see how the monsoon is progressing across the Indian subcontinent for this particular year 2022. So far I have discussed about all kind of the variability associated with the rainfall and how we can use the satellite data sets for the monitoring of such kind of the variability at inter-annual scale, intra-seasonal scale, extreme rainfall events, diurnal variability, and also the progression of rainfall using the satellite data set for every year. So with this, I stop this presentation, and